All right, ready to dive deep into sound waves.
Let's do it.
We've got this cool interactive simulation from a website called Open Educational Resources, Open Source Physics at Singapore. Kind of mouthful.
Yeah, but the website itself is incredible. It's like a playground for physics enthusiasts with tons of resources.
Right. I was just browsing and saw titles like Tracker Bungee Jumping Tiger Fox. Like, what even is that?
Yeah. And then you've got stuff like a 7.3.8.6 Earth-Moon escape velocity, potential one-dimension JavaScript HTML5 applet simulation model. They definitely don't shy away from the technical terms.
I guess not. Okay, but let's focus on the sound wave, longitudinal wave, JavaScript HTML5 applet simulation model for now.
Sure. So this simulation is all about visualizing how sound waves work, how they actually travel through the air.
Right. Before we get too deep into the simulation, maybe we should back up a bit. What is a sound wave, like, really?
Okay, so basically a sound wave is a disturbance, like a vibration, that travels through a medium, like air, by causing the particles in that medium to vibrate. It's kind of like...
Like ripples in a pond.
Exactly. Those ripples are essentially waves of energy moving outward. Sound waves are similar, except they are what we call longitudinal waves.
Longitudinal. What makes those different from, say, those water ripples?
Good question. In a longitudinal wave, the particles vibrate back and forth in the same direction that the wave is traveling. Imagine like a slinky.
Okay, I'm picturing it.
You push on one end, and the coils bunch up. That's what we call compression. Then they spread out. That's rarefaction. And this pattern keeps repeating.
So sound travels through the air in that same way, with these areas of high and low pressure, kind of like those slinky coils moving outward.
You got it. And this simulation actually lets us see this process. It shows those compressions and rarefactions as the sound wave moves.
Right. It's not just a static image, it's interactive. Which is way more engaging, I gotta say.
That's the beauty of it. You can play with different variables and see how they affect the sound wave. Like you can adjust the frequency.
Frequency. Yeah, that rings a bell, vaguely. Remind me of what that means in this context.
Sure thing. Frequency is basically how many waves pass a certain point in a certain amount of time. The more waves per second, the higher the frequency.
Frequency, higher pitch.
You got it. And the simulation really shows that relationship.
Wait, but hold on. If higher frequency means higher pitch, why does my voice sound so low when I try to sing high notes?
That's a great question. It has to do with how efficiently your vocal cords vibrate. When you try to sing high, your vocal cords stretch thin and vibrate faster, which means a higher frequency.
Right.
But if you don't have the proper technique, the tension can actually make them vibrate less powerfully, resulting in a weaker, lower sound.
So it's about finding the sweet spot, high frequency and strong vibrations.
Exactly. And this whole concept of frequency and how it relates to pitch is key to understanding why different sounds have different pitches. Like think about a deep bass guitar versus a high-pitched piccolo.
Okay, that makes sense. The bass has a lower frequency, longer wavelength, lower pitch. The piccolo, higher frequency, shorter wavelength, higher pitch.
Exactly. And the simulation lets you actually see those differences.
Okay, cool. But back to the website for a second. I get that it's got tons of resources, but does it really need stuff about Spotify and cyber wellness? Feels a bit random.
Yeah, I see what you mean. Maybe they're aiming to be a super comprehensive education platform, but it does feel a bit scattered.
Totally. And then their navigation, the breadcrumbs, they're like a comedy routine sometimes. You'll be in Newtonian mechanics, and under gravity, you'll find something about moon phases and tides.
It's definitely unexpected. But hey, at least it keeps things interesting.
True. So we've established that the simulation is pretty awesome, but why should our listener care? What's the big takeaway here?
I think the main takeaway is that sound, something we experience all the time, is actually a really fascinating and complex phenomenon.
Right. And this simulation gives us a chance to really understand it.
Exactly. It's a great way to learn about sound in an interactive way.
Totally. We're not just passively reading about it. We're messing around with the variables, seeing how it all works in action.
It's much more engaging and impactful.
Absolutely.
And by understanding sound waves, the basics, you can gain a deeper appreciation for music, for how we communicate, for the world around us.
Okay, I'm sold. Now, I'm really curious about those other crazy titles we saw on the website. Pendulum 3D JavaScript HTML5 applet simulation model, the 7.4.3.2 Newton's Mountain and escape velocity JavaScript HTML5 applet simulation model. Those sound wild.
We've only scratched the surface of this website. Back again. Ready for more on sound waves?
Definitely. Last time we were talking about how sound waves are those, what were they called? Longitudinal vibrations. And we
Uh-huh.
can see them in action with the simulation.
Yep. And it's amazing how easy it is to access tools like this these days. I mean, you used to need all sorts of fancy lab equipment to visualize this stuff.
Right. It's all right here in our web browser. Okay, so let's actually play around with the simulation a bit. What should our listener be looking for here?
So one thing to pay attention to is how the way it actually moves. Remember those compressions and rarefactions?
Hmm.
You can actually see them, those areas of high and low pressure, moving outward from the source.
And we can actually change things up, right? Like
Yeah.
there's this slider here for frequency.
Exactly. And this is where things get really cool. Remember, frequency is basically how many waves go past a certain point in a certain amount of time.
Right, and more waves per second means higher frequency.
Right. And higher frequency means
Higher pitch. So if we crank up the frequency in the simulation.
you'll see the waves get closer together and the pitch of the sound will go up.
Oh, cool. Okay, so like,
It's like imagine you're standing on a beach watching the waves come in.
okay, yeah.
If they're coming in really fast, one after another, that's like high frequency, high pitch. But if there's like a long pause between each wave,
That's low frequency, low pitch.
you got it.
I like that analogy. Okay, so it's not just a pretty picture. This simulation is actually letting us mess around with frequency and pitch and all that stuff.
Totally. And that's what makes these interactive simulations so great. You can see how things work in real time. It's way more impactful than just, reading about it in a textbook.
Right, it's like, okay, I kind of get the theory, but seeing it happen is like, whoa. Okay, that's what they mean by frequency.
Exactly.
This reminds me of when I was a kid. I used to play with a slinky all the time. I'd send those waves down the stairs. I was basically doing physics experiments.
You were. It's amazing how physics is all around us, even in a slinky. Sometimes you just need the right tool to help you see it.
So true. Okay, so we've been messing with the frequency. What else can we change?
Well, there's also amplitude.
Amplitude.
Yeah, amplitude is basically how intense the wave is, how much energy it has.
So higher amplitude means a louder sound.
Exactly. Think of it like hitting a drum.
Okay.
If you tap it gently, that's low amplitude, quiet sound.
Yeah.
But if you really whack it,
High amplitude, loud sound.
boom. Exactly.
Got it. So if we crank up the amplitude in the simulation,
You'll see the waves get taller, the peaks and troughs, and the sound will get louder.
okay, I think I'm really starting to get the sound wave thing. This is really cool.
It is.
And it's not just for, like, students, right? Anyone can use this.
Absolutely. Anyone who's curious about sound,
Yeah.
musicians, sound engineers,
Podcasters.
even just someone who, wants to understand why their voice sounds the way it does.
Yeah, totally. I'm thinking about all those times I've tried to hit a high note and failed miserably. Maybe my amplitude wasn't high enough.
Or maybe your frequency was off.
Probably a bit of both. This is really making me see sound in a whole new way. And you know what's even cooler? This whole website, all these simulations and resources, it's all free.
Yeah.
Yeah.
It's incredible. It's like they're making physics education accessible to everyone.
It's pretty amazing. You don't need to be in a fancy school or anything. You just need a computer and some curiosity.
And maybe a sense of humor, considering some of the names they come up with for these things.
Totally. Okay, so we've played around with frequency, we've messed with amplitude. What else can we learn from this simulation? Are there any other hidden gems in here?
Oh, there's definitely more to explore.
I'm back and still thinking about sound waves.
It's wild how much we take for granted,
Right, it's like we just go through life hearing things without really thinking about how it all works.
Yeah, totally. And we've learned so much already, how sound travels, how frequency and amplitude affect what we hear. But I feel like there's more to uncover. What else can we learn from this simulation?
Well, we haven't talked about the medium that sound travels through.
Oh, yeah, the medium. We talked about sound traveling through air, but can it travel through other stuff, too?
Good point. So sound actually needs a medium to travel. It can go through gases, liquids, solids, but it can't go through a vacuum, like space.
So those sci-fi movies where you hear explosions in space?
Yeah.
Totally bogus.
Pretty much. They're definitely bending the rules for dramatic effect. And this simulation, the simulation actually lets you see how different mediums affect sound. Wait, really? How does it do that?
You can actually change the properties of the medium in the simulation. You can make it denser or less dense.
Okay, and how would that affect the sound wave?
Sound generally travels faster through denser stuff. Think about how sound travels differently underwater.
Yeah, it's all muffled like underwater, and it seems to travel farther too.
Exactly. That denser medium, the water, lets the sound waves travel faster and more efficiently.
So in the simulation, if we made the medium denser, we'd see the sound wave moving quicker.
Right. And you'd also notice a change in the wavelength.
Oh, right, wavelengths.
Remember, the speed of a wave depends on the frequency and the wavelength. So if the speed goes up and the frequency stays the same, the wavelength has to increase too.
Whoa, that's a lot to wrap my head around.
It's pretty amazing how it all connects. And the simulation does a really good job of showing you those connections.
It really does. It's like, oh, that's how it works. This makes me think about echoes. Like when you shout in a canyon and the sound bounces back, is that because of how the sound waves are hitting the rock walls?
Exactly. That's reflection. When a sound wave hits a surface, some of its energy bounces back.
So the canyon walls are like giant mirrors for sound.
Kinda, yeah. And the shape of the canyon, that actually affects how the sound waves bounce back.
Oh,
That's why some canyons have, like, really crazy acoustics.
I'm learning so much. I never knew there was so much physics involved in an echo.
Right. Physics is everywhere.
Yeah. This website with all its simulations and stuff, it's kind of amazing.
It really is.
Even with those wacky titles, they've managed to like rekindle my love for physics. It's been a while since I thought about this stuff.
It's a great reminder that learning can be fun.
Totally. Okay, so we've explored the basics of sound waves. We've played with frequency and amplitude. We've even looked at how the medium matters. I feel like we could spend hours on the simulation.
We could, but unfortunately we're out of time for this deep dive.
Oh, man. But hey, we've learned a ton.
We have. As a final thought, I'd encourage you to think about how these sound wave principles we've talked about, how they apply to other parts of your life, music, the way you design your home, even how you talk to people.
So true. And don't forget, this website is out there, free for anyone to explore. So go check it out, dive in, see what you can discover.
Keep listening, keep learning.